Hello everyone. Today we're going to talk about the H2O2 decomposition kinetics along with a virtual lab. Today we're going to review a few concepts in kinetics. Even though we're not doing the experiment in the lab, I'm going to go over how the experiment was done. Then we're going to use the virtual experiment to obtain some data, and from this data I'm going to show you how to obtain the activation energy of our reaction. Let's quickly review some kinetics. So let's say we had some simple reaction A going to some products. We can represent this in a simplified rate equation. Rate equals K A to the M. A here is the concentration of our reactant. M is the order of the reaction of the species. K is the rate constant, and the rate is the rate of the reaction. Okay? Let's say we have some more generalized reaction, maybe species A plus B going to C plus D. We could write the rate equation like this. Rate equals K, A to the M, B to the N, where again M and N are the individual orders of the reaction for these two given species, and the sum of M plus N is the overall order of the reaction. K again is the rate constant, and this, the rate, is the rate of the reaction. Keep in mind, I'll probably say this a few times, but K is highly temperature dependent, okay? And of course, since K is temperature dependent, the rate of the reaction is temperature dependent. All right. Let's take a quick look at an example. Let's say I have some reaction A plus B going to C, okay? So I have some data here. So let's say I have experiment 1, 2, and 3. Here's the initial concentrations of species A, here's the initial concentrations of species B, and here's the initial rate of the reaction. I say initial rate of the reaction because what happens is over time, the data may start linear like this, but then it's going to kind of curve over. That's because the species begin to, the concentrations of the species decreases. Okay? All right. So we have this generalized rate equation. Rate equals K, A to the A, B to the B. Take a look at this. See how these two concentrations are the same for experiment 1 and 2? And look at experiment 1 and 3. Here I have this concentration the same and this concentration the same. That's rather convenient. So what we can do is let's focus on experiment 1 and 2 right now. We can use the rate equation twice. We can say rate 2 is K. We don't know K yet. We have the concentration of A, 1 molar, so we put a 1 there. We have the concentration of B, 2, so we put that there. Then for experiment 1, we do the exact same thing. Rate 1 is equal to whatever this initial rate is. The concentration of A is this, the concentration of B is this. So then if you take the ratio of those two, this bit will drop out. You'll have you'll have 1 to the A divided by 1 to the A, just 1. But it doesn't matter what A is as long as it's the same. Let's say this is a 4 and this is a 4. We'll have 4 to the A divided by 4 to the A. So this species will drop out, okay? So now I want you to use that to determine the rate constant based on this data here. Also determine the orders of reaction. I'm going to go over that in the next slide, but why don't you pause this for a minute and try to work it out on your own. All right, so I'm going to the next slide. So again, here's our generalized rate equation. What I said earlier is try to make two, focus on experiments 1 and 2 and try to make two rate equations. Rate 2 is K, A to the A, B to the B, okay? Rate 1 is K, A to the A, B to the B. And then you'll divide those two. So first, we have rate 2 over rate 1. Well, that's just this value here divided by this value here, which is a 2. And what I said on the previous slide is that the factors regarding this concentration of A will cancel out since these two are the same concentration. So then we have to focus on this here, okay? So this b to the little b, okay? So that would be 2 to the little b divided by 1 to the little b, which is just 2 to the little b. So then we have 2 equals 2 to the b So our b is 1. Our little b is 1. You do the same thing for rate 3 divided by rate 1. Okay, so we have rate 3 is 8 times 10 to the minus 2. Rate 1 is 2 times 10 to the minus 2, which the ratio is 4. In this case, the concentration of B is the same. It doesn't have to be 1 molar. It could be, as long as they're the same. Maybe it's 4 molar and 4 molar. The factors regarding the B, the capital B, will cancel out, and we're left with 2 to the A. How did I get 2 to the A? Well, it's 2 to the little a divided by 1 to the little a, which is 2 to the little a. So in this case, little a is 2. The overall order of the reaction is 1 plus 2, which is 3. Now you can back solve to get K. So you look at this. We have little a is 2, we have little b is 1. Okay? Then you just pick any of the experiments. Let's say 1. So you put the initial rate here, you put the concentration of A there, the concentration of B there. You have everything you need except K. You just solve for K and you get K. You can do that for experiment 1, 2, and 3, and you'll get the same K. What I didn't write here, which I should have, is that the experiment 1, 2, and 3 are at the same temperature. If they're not at the same temperature, then this won't be true, okay? If you have a variable temperature, you have to use a Arrhenius equation, which we'll see in several slides, okay? So very important, make sure you know how to get K. Okay, we're not doing this actual experiment this semester since we're remote, but I want you to know how we would have done it, okay? So we have this Erlenmeyer flask here, and we have a stopper. We put our concentration of H2O2 in here along with some extra water, okay? We have a syringe, okay? We would add our concentration and amount of Ki to this syringe, okay? We have this connected to a vacuum pump. We would pump down to maybe 45 millibar in here. We would stop, we would block the pump. Then we would inject our Ki. What is interesting is if you ever do this, is you don't need to actually push on the plunger. The vacuum will just suck the Ki into there, okay? Then the reaction proceeds. What's happening in the reaction is that the H2O2 is decomposing under an I- catalyst, okay? So oxygen is being liberated. Since oxygen is being liberated, the pressure in here is increasing. We have this hooked up to a pressure gauge, and you can read off the pressure gauge the increase or the change in temperature in the flask as the pressure increases. Okay, so you would do that for 3 experiments, and then you notice it's sitting on a hot plate. For the 3rd experiment, you would heat up the solution to maybe 35 Celsius. That number is up to you, okay? And you assume that these, for the first 3 experiments, are at room temperature, roughly 25 C. Okay, so I basically just said this, but in more details. Here is how you would. Here are the trials 1, 2, and 3. The temperature, or at least suggested temperature of the trials. You can, if you do this in lab, you can pick in. Well, these 3 have to be the same room temperature, but this you can modulate to anything you want. You would add this amount of H2O2 each time to the flask, along with this amount of water. Okay. Eventually, you would inject this amount of Ki into the flask. At the end, these are the concentrations. After these 3 are mixed, these are the concentrations. Let's call these the initial concentrations of H2O2 and Ki in the flask. Remember I said earlier that the initial concentrations are going to change as a function of time since the H2O2 is decomposing. Okay? You do runs 1, 2, and 3 at the same temperature. Again, then you elevate run 4. I'm going to mention this again, but if you're ever doing this, here we're using 30% H2O2. It's fairly corrosive. It could blind you, so you must wear goggles. It can it can damage your skin. You must always wear gloves. And the hot plate will get much, much hotter than 35C. So you have to be careful not to touch the hot plate with your hands. Okay, just some tips. Don't let the pressure get too low in the flask. If you let the pressure get too low in the flask, it'll start decomposing the H2O2 before you inject the Ki. So you should keep the room temperature runs about no lower than 45 millibar, and the elevated temperature run, if it's about 35C, you should keep it no lower than 65 millibar. If you are pumping down and you start to see bubbles in your flask, well, you have to start over. Your H2O2 has begun to decompose. That error happens often at elevated temperatures, since depending on the temperature of your solution, the H2O2 will break down at higher and higher, before you get to lower pressures. Okay. So, my word run 1 did not want to appear. Oh well. Okay, so again, this is the experimental data. So, the values we will enter. Okay, so this is examples of your data. Okay, so you're going to measure the pressure increase as a function of time. So again, you have your solution, you inject your Ki. You had a blue pressure gauge which would read off the pressure in millibar. That pressure would slowly increase, okay, as you would measure it every 5 seconds, let's say. 0, 5, 10, 15, so forth and so on. Then you would write down the pressure. Then you would make a graph, time, seconds on the x-axis, pressure millibar on the y-axis, okay? And then you would fit a linear to the initial part of your graph. Now, the data, if you would do this in lab, won't look perfectly straight like this, okay? It would look straight for, some time and then begin to bend over, okay? That's because you're decomposing your H2O2 and you're not going to get any more oxygen liberated into your flask, okay? So your data in the lab would not look this perfect, okay? And again, so what you do is you plot your data, you fit a line to it, and you get a slope. The slope will be in millibar per seconds, but that's really not convenient for the rate equation. We don't want millibars per second. We want maybe molarity per second. Okay, so we have to somehow convert this millibar into molarity. So how do we do that? We'll use the ideal gas equation. Okay, so again, the gas we're liberating is oxygen, which is pretty reasonably assumed to be an ideal gas. Okay, we'll use the ideal gas equation. Okay, we have PV equals nRT. We divide by RT, so we get something moles per volume. Okay, and that's what we want in addition to seconds. Okay, so we start with our slope. Let's say, as an example, we have 2 millibars per second. Okay, we don't want that. We want something molarity per second. So first, we convert millibar to Pascal to get that into. We're going to use SI units with this for convenience. Okay, so we have this in now pascals per second. We divide by RT. Okay. R is in 8.31. Temperature is in Kelvin. Be careful for runs 1, 2, and 3. It's something like 298 Kelvin, but your elevated temperature run may be 308 Kelvin. Okay. Now this is in SI units. So the SI units of volume is meters cubed. We don't want that. We want liters. So we convert this from meters cubed to liters, so we divide by 1,000. And then we get something we want, molarity per second. That's what we want for our rate equation, okay? So you do this for rates 1, 2, and 3, okay? And then you do it again for run 4, except again for run 4, the temperature will be 308 Kelvin, or whatever elevated temperature you use. I'm actually going to come back to this at the very end, so you'll understand in a little bit. Okay, so now there's a couple ways to do this. We know how to get our rate 1, 2, 3, and 4. We have to get our we have to get our rate constant 1, 2, and 3. Okay, we will later we'll get our rate constant 4, but again that's at an elevated temperature. I'll get to that in a little bit. Okay, we also need our orders of reaction. Okay, so there's a couple ways to do this. We could do the way we did with that problem earlier in the lecture slides, or what we can do is, again, we have our rate equation. Let's say rate 1 is equal to now K1, 2, and 3. They're going to be, well, it's experimental data, but they'll be very, very, very close to each other. Here's our concentration of our H2O2. Here's our concentration of I minus, our catalyst, and A and C are our orders of reaction. I chose the letters A and C not to confuse anything with y equals mx plus b. Okay, anyway, we take the natural log of both sides. Okay, so we have natural log of rate equals a natural log of concentration of H2O2 plus c natural log of I minus plus natural log of k. Now, let's say we're looking at 2 runs where I minus is fixed. Okay, maybe rate 1 or maybe 1 and 2. If I minus is fixed, then this is fixed. And of course, since the temperature is fixed, this is fixed. And so since C is a constant, this whole little bit here is fixed, okay, for 2 runs where I minus is fixed. So we have something that looks like Y equals mx plus b. So you can plot the natural log of rate on the y-axis versus the natural log of the concentration of H2O2 on the x-axis, and your slope will be A. You do the same thing while varying I minus, and you get C. Okay, then now you have your orders reaction. Okay, you put that here and that here. You pick any one of the runs. Well, actually, do it for all 3 of them. So do it for rate 1. You have your rate. You have concentration of H2O2, you have concentration of I minus, you get K. Do the same thing for rate 2 and 3. You'll find out that the Ks are very similar. The K I'm looking for is the average of those 3. Write that down, but again, it'll be very similar. K for run 4, K4. So here's our Arrhenius equation. We take the natural log of both sides. Okay, so we have the natural log of both sides. Remember, the natural log of E is just whatever the exponent is. So we have natural log as K is equal to minus activation energy over RT plus ln of A. Now, in this, we're going to have to assume that this prefactor A is independent of temperature. Not really true, but for the purpose of this experiment, assume that A is independent of temperature. Okay, so in this case, we plot natural log of K on the y-axis versus our x. But in this case, our x is 1 over t. Okay, the slope is minus E over R. You will get a negative slope. So a negative slope is equal to negative E over R. Okay, then you just multiply by R and you get the activation energy. Please don't give me a negative activation energy. The activation energy is a positive number. In the past, many students gave me a negative activation energy. Please don't do that. Okay. This is a quick problem. This is just from your general chemistry books. I just want you to recall. So let's say we have 30% hydrogen peroxide. What is that in terms of concentration? Okay. I give you, let's say the density of the solution is about 1 gram per milliliter, and I give you the molecular weight of hydrogen peroxide. Now try to calculate the concentration of the H2O2 in the bottle. The hint is trying to think what to do with this 30% hydrogen peroxide by mass. Okay, well, what does that mean? Okay, so pause the YouTube video and try to work this out for a minute. All right, let's see. So again, what does that 30% hydrogen peroxide by mass means? That means I have 30 grams of H2O2 per 100 gram solution. Okay, so I then tell you I tell you the density in solution is about 1 gram per milliliter. Okay, so I use that here. The grams of solution and the grams of solution cancel out. Okay, So then I can use the molecular weight of hydrogen peroxide, 34 grams per mole here, okay, or excuse me, the inverse of it, okay, since I have grams for H2O2 here and grams for H2O2 here. So then I just convert milliliters to liters, and I have the concentration of the H2O2 in the bottle, okay? So 30% hydrogen peroxide is about 8.8 molar. Okay. Now, we're not doing this lab in, we're doing a remote lab this semester, but I just want to remind you of some safety. So the hot plate will get very hot, at least the one we use in the lab, so don't touch it. The surface will burn you. It might have burned me at one point. The 30% H2O2 can blind you, and it can also damage your skin, so everyone must wear goggles and gloves. Incidentally, everyone must wear goggles in every lab. Okay, now to the virtual experiment. If you click on this link here, I'll put it in the description below, it'll take you to the virtual lab. All right. Okay, so here's the virtual lab. All right, so all you have to do in the virtual lab is enter the volume of H2O2 that you're going to put in your flask, the volume of additional water that you're going to put in your flask, and the volume of Ki that you'll inject into the flask along with the temperature in Kelvin. So let's try this for run 1, okay? So we have 7.5 milliliters of H2O2. We have 2.5 milliliters of Ki. We have 15 additional milliliters of water, and temperature, be careful in Kelvin, 25C is about 298 Kelvin. So you hit enter, okay? And then I even tell you the final concentration of, the concentration of H2O2 at the beginning of the reaction and the concentration of Ki at the beginning of the reaction, specifically the concentration of I minus. So then I spit out the data for you, okay? Behind the scenes in the code, I have the equations embedded, so you can, you can play around with these if you want. Anyway, so here is your data. Okay, so now what you need to do is you need to extract this data. So we copy it, okay, and then we paste it here. Edit, paste. So now see, now there's a comma there. We don't really want that, so we go to comma, split text to columns. Okay, so it gets rid of the column. So now let's plot this. Insert chart. Hello? Let's try that again. Oh, there it is. Okay, change this to scatter. There's our graph. Again, on our x-axis, we have time in seconds, and on our y-axis, we have pressure in millibar. So let's add a tread line. Okay. Let's remember how to add a tread line. Yay, can't remember. Come on. All right, there we go. And okay, we have a tread line and we have our equation. The slope is 1.24 millibar per second, okay? So remember what I said. I would go back to the lecture slides and tell you again what to do with that 1.24. So let's go back to the lecture slides. Right here. All right? So our first one, we have 1.24 millibar per second. We multiply by 100 to convert millibar to Pascal. We divide by RT. R is 8.31. T, again, is dependent on your run. For run 1, 2, and 3, it's about 298 Kelvin. But for run 3, it's about 308 Kelvin. You can change that if you want. We're in SI units. We convert meters cubed to liter. And we have our first rate in molarity per second. You do that for rate 1, 2, 3, and 4, and you have your 4 rates. From your 4 rates, well, from your first 3 rates, you get K1. Okay, for rate 1, 2, 3, you get K1, K2, K3, which are about the same. For rate 4, you get K4, which is much higher. Okay, you take the average of K1, 2, and 3. Okay, and then you just use Arrhenius equation you get 2 points. Let's say one point at the room temperature K, and then another point at the elevated temperature K. Okay, so you just have 2 points. You fit a linear to that. Oh, excuse me, it's going to look like that. The slope will be negative, okay? And the slope is equal to negative E over R, and you solve for E activate, the activation energy, and the activation energy is positive. Please don't give me a negative activation energy. All right, that's it. Thank you.